Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our analysis and design software, RSTAB. The topic for today's webinar is nonlinear time history analysis with machine-induced vibrations. My colleague Gerlin Schubert will be your presenter. She's a product and customer support engineer located in Leipzig, Germany. My name is Amy Heilig. I'll be your moderator. I'm the CEO of the U.S. office and also a technical support and sales engineer located in Philadelphia, Pennsylvania. Finally, my colleague Stefan Frenzel will be answering any questions you may have. He's a product and customer support engineer located in our Leipzig, Germany office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the webinar. You can do so within the same dialog box. If by chance we don't get to all your questions, we will certainly send you a follow-up email afterwards. So regarding the content for the next hour today, I want to quickly go over the overview and features of our DYNAM Pro modules within our main programs RFM and RSTAB. And today we'll be focusing on the linear and nonlinear time history analysis within these same DYNAM Pro modules. We'll move on to an example within RSTAB. This will be machine-induced vibrations on a structure. We'll take a look at the natural frequency analysis as well as the deactivation of tension-only members. From here, we'll move on to a linear time history analysis and see how resonance affects this same structure. And lastly, moving on to nonlinear time history analysis, we'll see how we can take into account those nonlinearities such as tension-only members and failing supports. So we have several modules when it comes to dynamics within our main programs RSTAB and RFM. The first is DYNAM Pro Natural Vibrations. So this is a prerequisite for any of our other dynamic modules. We must determine what the natural mode shapes and frequencies of our structure are. From here, we can move on to DYNAM Pro Force Vibrations. Now this allows us to run a linear time history analysis within the program. You can see this graph here is a time course monitor. So this is for a tension-only member and we're viewing the normal forces for that member. Now, because this is linear time history analysis, you'll see both tension and compression forces within this tension-only member. Now, we can also perform a response spectrum analysis. We won't be getting into this portion today, but just to let you know that is available as well. Now, recently added is the DYNAM Pro Nonlinear Time History. So this is a module extension to the Force Vibrations module. What this allows us to do is to take into account those nonlinearities. So as you can see, this is that same time course monitor shown here for that tension-only member. Because this is now a nonlinear time history analysis, we should no longer see those compression forces within the member. And as you can see in the time course monitor, we only see tension forces here. Lastly, we have our DYNAM Pro Equivalent Loads module. This allows us to perform a response spectrum analysis with the export of equivalent loads. We won't be getting into this module today, but just to let you know, we do have a couple other recorded webinars available on our website and our YouTube channel that we'd like to refer you to. Now, with that said, I want to go ahead and turn it over to my colleague Gerlin for the rest of the presentation today.
Many thanks, Amy, for the introduction. So I will start straight away and give you some more details to the DYNAM Pro modules and especially the time history solvers. Let's start with the DYNAM Pro Natural Vibrations. So as the name says already, this is for analyzing frequencies and mode shapes. You can import masses directly from load cases, and you can combine masses and mass combinations. You have different mass matrix available, but the most important thing for today is the stiffness modification feature that I want to show you today. We want to use this to study some failure of tension members. So how are frequencies actually changing when tension members are available or when we deactivate them? So The eigenvalue analysis is a linear analysis, and this means all the tension members are replaced by truss members. They can cope with compression as well. And to study changes in frequencies, you have to act here you have to do things manually here. You have to deactivate these members. And this is what I want to show you with the DYNAM Pro natural vibrations today in the example that follows. And now I want to tell you a few things about the time history analysis. We distinguish in DYNAM Pro between linear time history analysis and nonlinear time history analysis. That's what Amy already explained very well. So the linear analysis neglects structural and geometrically nonlinearities. So, for example, tension members or cables are replaced by truss members, or they are simply ignored. So if you, for example, define a failure of some supports, this is then a fully acting support instead. The linear analysis is a first order analysis, so it considers the small deformation theory. And we have two solvers available, the modal analysis and the implicit Newmark solver, but I go a bit more in detail and explain the solvers in the upcoming slides. The nonlinear time history analysis is in RFEM, a large deformation analysis. In RSTAB, you have both types of analysis available. You can apply the theory of small or large deformations. All nonlinearities that are defined in the model are considered also in the time history analysis. So here again, we have also in RFEM, we have two solvers available, the explicit and the implicit solver. I go in detail to this. And at RSTAB, we have the explicit solver only. We further distinguish between the time history analysis of time diagrams and oscillograms. The time diagrams can be defined as tabulated values as a periodic function, or you can enter a function term directly in an added field. You define loads and load cases to define the location of the excitation. So this makes it very flexible. So you can define nodal member loads, surface loads, or even free or generated loads. So you can excite the structure everywhere, wherever you want. And time diagrams and load cases are then connected together in the dynamic load cases. And using this, you can even simulate an excitation that varies not only over time, it can also vary over position. The time history analysis of oscillograms, this is an excitation at supports. And the acceleration time diagrams can be imported from a library of earthquake recordings, or they can be user defined. And we have the multi-point option available for the linear analysis. So the modal analysis, now I concentrate really on RSTAB, DYNAM Pro today. And the modal analysis in RSTAB is based on a decoupled system. So you really need a certain amount of eigenvalues. This is required to ensure the accuracy. And how can you know whether or not you have enough eigenvalues? You can have a look to the effective modal mass factors. And it's also important to compare natural frequencies of your structure and the excitation frequency that you have. DYNAM Pro offers an analytical solution of single degree of freedom systems here. So as you find it in the literature, so you have closed solutions for periodic excitations and a Duhamel integral for arbitrary excitations. The mass matrix and stiffness modifications are taken from the natural vibration case that you defined and assigned. You can define Lair's damping values differently for each eigenvalue. We have initial deformations available. And this is very interesting. We offer the steady state response for periodic excitations. This is only available with the modal analysis. So instead of the complete solution of the differential equation, here only the particular solution is provided. And the modal analysis offers a static correction. This means in case there are any missing masses due to not calculated eigenvalues, DYNAM Pro is able to add those in a pseudostatic way. So this is recommended for structures with high frequencies beyond the rigid frequencies. And because for such frequencies, only the steady state response is expected and added to dynamic analysis. So instead of calculating an enormous amount of eigenvalues to reach some amount of activated mass, you can instead use also the static correction feature. Also only available for the modal analyzers in RSTAB. The second solver we offer is the implicit NUMAC solver. This is a direct time step integration. So here you do not need any eigenvalues. You do not have to assign natural vibration cases. Instead, you have to ensure a quite small time step. The time step is important for the accuracy of the results. And there is a recommendation that you find in the literature. It's provided here as a formula, so 1/20f, the frequency. And here you need to consider the natural frequencies of your structure and also the frequency of your excitation. Both is important here. The dynamic load cases with direct time integration solvers have their own calculation parameters, and in there the mass matrix and stiffness modifications are defined. So because you do not assign any natural vibration case, you have own calculation parameters for those cases. The direct integration solvers, they require the Rayleigh damping as a structural damping, so you have the Rayleigh coefficients alpha and beta. We discussed today in the example how to convert from layers damping values, these are usually the values that you find in the literature, to the Rayleigh coefficients. So also offered as the initial deformation, but as I said, the steady state and the static correction is not available for this solver. So now the nonlinear solver. This is also a direct time step integration scheme, so eigenvalues are not required and natural vibration cases are not assigned. All the nonlinearities that are available in RSTAB and that you defined in your model are considered in the nonlinear time history analysis. So you have in the global calculation parameters, you get an overview about all the nonlinearities that are available in the main program. And depending when you have defined them in your model, the checkboxes are active, and otherwise they are deactivated. So, and we go into detail here. We have several member types that are nonlinear. These are the tension only, compression only member types, buckling, and cable. Then you can define member nonlinearities for each type of member, a beam, for example. So you can define plastic hinge options or some yielding or failure. You can also define nonlinearities for supports. So you can define several conditions. You can define frictions, or a quite flexible one is the diagram of partial activity. And similar, these things are available for hinges, for release conditions. In RSTAB, we have also the foundation of members that can be inactive, also it fails if negative or positive contact stresses are available. RSTAB considers small or large deformations, so you can apply both theories. And the RSTAB solver is explicit, but it contains some elements of an implicit solver to stabilize the solution. In the linear case, the calculation is stable independent of the time step, but RSTAB automatically determines the time step that is needed for calculation, and it uses the omega max. This is a frequency, a maximum frequencies. You can change this value in the detail setting of DYNAM, but the default value is quite okay. So this is just if you really think you need a smaller time step, but the automatic option here in RSTAB is working very well. And when nonlinearities are defined during the calculation steps, RSTAB is able to reduce the time step further. It's automatically reduced as soon as nonlinearities are detected. And RSTAB does not use a constant time step. Instead, the time step is optimized during the calculation steps. So you do not provide any time step for calculation in case of the explicit solver. RSTAB is doing this automatically. As with all the other time integration solvers, you define the mass matrix and you have the stiffness modifications available, and you can, it's again the Rayleigh coefficient that are used, and you can also define initial deformations. So the user interface of linear and nonlinear time history analysis is basically the same. It's just the solver that is added when you have the add-on module nonlinear time history. I just want to quickly discuss the differences to RFM. In RFM, we offer two solvers for the nonlinear time history analysis. We have the implicit Newmark solver and the explicit solver. RFM offers the large deformation analysis, and the explicit solver is best for short time excitations. So for example, impulse or explosions. And it's a conditionally stable process. So the time step needs to be smaller than the stable time increment. And this stability limit is determined with the smallest finite element length. And here the formula is provided, but the omega max is not known by RFM itself. So it's approximated with the smallest finite element length. This is the automatic time step evaluation, but you are allowed, and it's often required in RFM, to determine an even smaller time step, to define an even smaller time step manually. The explicit solver in RFM has some restrictions. It's only working for a diagonal mass matrix and also for a diagonal damping matrix. And for the damping matrix, this means you can only define alpha damping. The beta needs to be 0. These are restrictions, but RFM is far more complex. It has more non-linearities available than RSTAB, obviously. It's a finite element program, and RSTAB is a truss analyzer software. The implicit solver is unconditionally stable, independent of the time step, but still it's very important to use small enough time steps to determine accurate results. And I recommend in RFM always to do a convergence study for the time step. So let's go to the example. I think that's enough for all the theory and solver difference. So let's jump over to RSTAB directly, and that's the structure we are looking at. Some of you might know it. It's the example that we have in the manual. Here we perform a linear time history analysis, and today we will do some different case studies and perform also nonlinear time history analysis. So that's a simple steel structure. I've defined some tension members here. So the bracings are tension members, and the machines are sitting here in the openings. So I've defined two load cases, the self-weight of the structure and the self-weight of the machines. And here you see where the machines are based. So I've defined just the load arising from the machines. I did not model the machines itself. And these are member loads that I've defined here. So let's get started with DYNAM Pro. First of all, we want to perform a natural vibration analysis. And therefore, I also want to combine some masses. Later on, we also activate the linear time history analysis of time diagrams and the nonlinear time history analysis. But we go through it step by step and start with the natural vibration analysis. So I'm going to define a mass case. That's the first one, and I do not want to consider the self-weight automatically here. I want to import a load case because in the load case 1, there are some additional loads defined. And the second load case, mass case, is the self-weight of the machines. And here I want to import the load case 2. On the right-hand side, you always get a summary of what masses you imported, and this is nice, and you can double check if it's the masses you expect. In the mass combinations, we combine the two mass cases, and you can just add all mass cases, and they jump over to the right, and this is then the combination, so all the complete self-weight. So when I use factors of 1, this is automatically done because I've chosen a mass case type permanent here. There are some other mass case types available, and the combination factors are then adjusted in accordance to the Eurocode 8 part 1. Natural vibration case. So to emphasize this again, it's a linear eigenvalue analysis. So our tension members will be replaced by trusses. So I give it that name just that we keep in mind. And I want to analyze, I want to have a look to the first 10 eigenvalues. I would not actually need to calculate the eigenvalues because I'm going to use direct time history solvers. So they do not require any eigenvalues, but it's very important to understand the structure. You have to know the dominant eigenvalues of your structure, and also you have to study cases of resonance. And that's why it's very important to always calculate your eigenvalues. It's the basic. So I want to import the mass combination that we have defined. Let the masses act in all directions. And today we are going to use the diagonal matrix. I've double-checked the consistent matrix in advance, but there's not much difference in this simple example here. So we are going to use the diagonal matrix. So everything else, we keep it as it is. Later on, we will use the stiffness modification feature, as I have mentioned in the introduction. So that's all for the natural vibration analysis, and I'm going to calculate this. And now we have the graphics of we see the mode shapes, and we have the tables, and the results are all available down here. At the moment, we have only one case calculated, the natural vibration case 1, and you can switch between the several mode shapes, either here with the drop-down, or you can just click in the table, and the graphic is automatically updating. So let's have a look. We have the eigenvalue number 1. It's 1.2 Hertz. And this is obviously, when we just look to the graphic, and mode shape acting in the Y direction. We can also double check this by looking in the effective modal mass factor table. And you have here the effective modal mass factors. And here you see the mode shape 1 activates 72% mass only in the Y direction. So this is definitely, this is a dominant mode shape in the Y direction. Then there are a few more eigenvalues in the Y direction, but all not as important. This one is a little bit important, 18% mass, but this is clearly the dominant one. And in the X direction it's even more clear. We have the eigenvalue number 6, which activates 89% mass in the X direction. So let's have a look to the frequencies again. So we have 1.2 Hertz in the Y direction and 3.9 Hertz in the X direction. These are our two dominant eigenfrequencies when we consider the structure completely linear. So all the 4 tension only members can cope also with compression. So we go ahead studying this linear. So now we did a linear natural vibration analysis, and I'm going to show you first the linear time history analysis, and we want to excite the structure with time diagrams. So I'm activating the time diagrams, and you see now 2 more tabs appearing here, the time diagrams in the dynamic load cases. In the time diagrams, we want to define periodic excitations today. And in the dynamic load case, here is the place where you combine load cases with time diagrams. And I'm going back to the slides, and I want to discuss the machine-induced vibration. So we have to talk about the excitation first before I enter all the data in here. Otherwise, you might not understand what I'm actually doing. So I'm going to the slides, and there are many different types of machine-induced vibrations, of course. We look into a rotation of an unbalanced mass today. The unbalanced mass is rotating with 235 rounds per minute. It has a mass of half a ton, and the eccentricity is 0.65 millimeter. So we can calculate the excitation frequency. That's just a simple unit conversion from rounds per minute into radians per second or into hertz. So we have an excitation frequency of 3.9 hertz. So, and everyone who have just listened to the natural frequencies, and I have chosen the excitation in a way that we definitely will have a case of resonance today when we study the structure linear. So we had a dominant natural frequency in the X direction of 3.9 hertz, and we have also an excitation frequency with the same value. The radial forces are calculated with the given formula here, and we have 179 Newton. And to explain you now the connection between the time diagrams and the actually rotating of our unbalanced mass, these are the time diagrams that we are going to define in DYNAM. So we will enter the frequency here, the 24 radians per second. The vertical component will have a shift of 0. So it starts, it's a sinus function, and we have a multiplier here, which is 1. This is really a multiplier which multiplies the time diagram with the load in the load case. So it's up to you whether you have a value in here, which is unequal 1, or in the load case. I decided having a multiplier of 1 in DYNAM and define the 179 Newton in my load case. The horizontal component is just shifted by a quarter circle. So it's the same, the frequency is the same. I've entered a shift here and I have the same multiplier. And now, what does it actually mean? So we will define horizontal forces and vertical forces in load cases. And we will connect these to the two time diagrams. When we look to the time which is equal to 0, the vertical component will be 0 and the horizontal component will be fully available. And this is indeed the case. We have a horizontal force and no vertical component. Going ahead to the next step, we have now a full vertical load and a 0 horizontal component. So this is indeed the case. And all the stages in between, so because the mass is going around the circle and the radial force as well, so all the cases in between are now covered by our time diagrams. We can go ahead, look to the other cases. Here we have a negative horizontal component and a 0 vertical component. And at the bottom of the circle, we have a negative vertical component and a 0 horizontal component, and so on, rotating along. So we are going back to RSTAB and defining this in the program. So we have to define load cases first. So I close the DYNAM Pro module. I go to the Edit Load Cases and Combinations dialog. The button was up here. And I'm going to define a new load case, which is the radial force vertical. And I'm going to define some member loads acting in the global Z direction, so vertically, and the 179 Newton that we have seen in the slides. I want to apply this to the members around the openings here, and these are 4 members, each 2 meters long. So I divide the 179 by 8, and this makes 24.6 Newton per meter. And I'm just selecting now the members in the graphic, and the same down here. And just right click to finish this process. And I'm going again into the Edit Load Cases and Combinations dialog and copy my load case that I've just created. I copy it. I change the comment up here to horizontal. And all I have to do now is changing my loads. So we have table 3 here that contains all the loads, and we have defined member loads. And you can either directly change it here. That's the easiest. We just change the direction here in X, global and X direction. You could also double click on the row and the dialog would open again. So it's now acting global in global X direction. So we have defined now the loads. So we have defined the location of our dynamic excitation. We have a vertical radial force and a horizontal radial force. And we go back to DYNAM and define the time diagrams as we have seen it in the slide. So we have the vertical component. That's vertical. And I copy this and define the horizontal. And this is just a shift here. You can also enter it in degrees if you prefer. So you have the unit and decimals dialog down here, and you could change it to degrees. So that's the shift by the quarter circle. And now we are going to connect them both. So the radial force in vertical direction comes together with the vertical time diagram, and the radial force in horizontal direction comes together with the horizontal time diagram. So we have to do a few more settings for the linear time history analysis. We want to use the linear implicit numeric solver today. And here in the time history analysis tab, we still have to define the time steps for saving and also the time steps for calculation. I want to save time steps every 0.01 seconds, and I want to perform the analysis up to 10 seconds. And here the implicit solvers, they can determine the time step automatically, but here the time diagrams are used because DYNAM Pro does not know anything about the eigenvalues right now because we did not assign any natural vibration case. It can only use the time diagrams for evaluating here the automatic time step. So it really depends on your example. In our case, this would be okay, but when you have natural frequencies of the structure that are larger than your excitation frequencies, you definitely have to do it manually. And this is basically just the formula that you have seen in the slides earlier, 1/20f frequency. And when I calculate this, I end up with this time step. It's even smaller because I have defined my save time step this way. The save time step is just, this is just for a smooth curve later on. So if you want to have a smooth graph, a time course graph, then you have to reduce the time steps here. If you do not need this, then you can increase the time steps because this saves, of course, memory and calculation time because also the saving takes some time. Okay, calculation parameters. We want to import the mass combinations. We want to let the masses act in all directions. And here we do not consider any stiffness modifications. The damping, this is another topic that we have to discuss before we perform the calculation. In the literature, you usually find layers damping values, and I want to damp my structure with 1% Bayes damping today. And so I have to calculate the Rayleigh coefficients myself because I have dominant frequencies, which is the first one and the sixth one. So I have really to calculate alpha and beta myself. And this is not very complicated. We are just going to see this and double check this in the slides. So our dominant frequencies, we discussed this already. We have 1.2 Hertz and 3.9 Hertz in the Y and in the X direction. And layers damping and Rayleigh coefficients are connected with this formula. And all we have to do now is entering all the values we know. And I want to achieve 1% layers damping. And I just enter my frequencies, so in radians per second, because that's omega here, that's the angular frequency. And so I end up with two equations and two unknowns. That's a system of equations which you can easily solve. And what you get is it's the solid black line here. That's the Rayleigh damping containing alpha and beta. So I've calculated now an alpha of 0.12 and beta is 6.2 10 over -4. And you see the green lines show the dominant frequencies of our structure. So you see I have adjusted alpha and beta that way that we have exactly 1% Bayes damping for the frequencies that we really want to damp that way, because these are the dominant frequencies. And the nature of the Rayleigh damping is that it does not damp the frequencies all equal. the damping is different for each frequency. And the dashed and the dashed dot line, these are just for illustration. So it's the dashed one is here alpha is set to 0, and the dashed dotted line is here beta to 0. It's just for, that's the graph you usually find also in the literature. If we have now frequencies between the two, they are lower damped, and if you have frequencies lower or higher than the 24 radians per second, then they are slightly overdamped. Okay, back to the RSTAB. We enter our values that we have just calculated. So we have 0.11686 for alpha, and we have 6.1 10⁻⁴ for beta. And now we are ready to calculate the linear time history analysis. Stop. I wanted to create a result combination just to show you that this is possible. So you can generate load cases for single time steps, result of single time steps, and you can create a result combination which gives you maximum and minimum results, so an envelope over the whole analysis time. And it's exported to the main program and can be used then further for design. So I calculate this. And now that's the dynamic envelope that we just see. I increase the tables a bit. You have now two cases available here, the natural vibration case 1 that we had earlier, and the dynamic load case 1. And here in the right drop down, you have results of all single time steps, and you have the dynamic envelope. Most important is the time course monitor, which is accessible here. So I open this in an extra window, and now this is interactive, so you can click on a node in the structure, and the time course monitor jumps to this node and shows the results. Now we look at the displacement in X direction, and the curve clearly shows that we have a resonance here. So the results are increasing over time. This only happens when a resonance occurs. So our natural frequency of the structure is identical, nearly identical to the excitation frequency, and this leads to a resonance. So this is something we really have to avoid, and we have to change something here. But remember, we did a linear analysis so far. That's not what the structure is in reality. So when we have a look to the tension only member, I have to switch to the normal force and display position. So here you see it's a tension only member, but it has tension and compression forces in it, and they are increasing because of the resonance. So how can we, the first question is, how are the frequencies changing when tension members are not available, when they fail? How can we do this? How can we analyze this in RSTAB? So, and I've already mentioned the stiffness modification option that we have in the DYNAM module, and therefore we have to define a load case first. And I want to define a load case without any loads. It's basically an empty load case. It's just to deactivate some members. So I deactivate tension members in this load case in the plus X direction. And you find this option here. You select modify stiffness, then another tab appears, and in here you have deactivate members. So we can pick them graphically, and let's have a look again to the natural vibration case, and let's have a look again to our mode shape in the X direction. That's the dominant mode shape in the X direction. And when we look now to this deformation state, we can clearly see which members are failing. This tension member and this tension member shouldn't be available when we have this deformation state. So I'm going to deactivate them in an empty load case so far. Okay, now we go back to DYNAM Pro. And in here, in the natural vibration cases, I have the feature stiffness modifications and can import here load cases. I can import axial forces, I can import failing members, stiffness modifications, and also deactivated members. I'm going to copy the natural vibration case. And now this is the case that we study of failure of tension members. In plus X direction, you could have several natural vibration cases here and study different cases depending on the complexity of your structure. In our case, it's quite clear, but I could also consider the minus X direction. So here in the webinar today, we consider only one direction. I import here the load case 5. And I really didn't want to have any loads in the load case because this feature also imports axial forces. So it imports a geometric stiffness matrix. And if you do not want to have the influence of any normal forces, then you should create an empty load case and just for the purpose to deactivate some members. So I calculate the natural vibration case 2, and we will see how the frequencies are changing when the tension members are not available anymore in this direction. So we still see the 1.2 Hertz that we had before. This is our frequency in the Y direction. This stays unchanged, and it should be because we didn't change anything in this direction. And we have now here a different frequency number 1. And this is now clearly our eigenvalue in the X direction. Let's have a look to the effective modal mass factors. We still see the 72% in the Y direction, unchanged compared to the original. And we have now new and dominant eigenvalue, which activates 83% of mass. And this is now a changed frequency. So we have only 1.1 Hertz now in the X direction. It moved back from 3.9 down to 1.1. So this is nice because we do not expect any resonance here. So it's really worth to consider the structure with non-linearities. So it's important to consider the tension members. We go back to the DYNAM and perform now a nonlinear time history analysis. There's not really much to do. We just have to activate nonlinear time history in the general tab. And we again want to excite the structure with time diagrams. And the user interface stays the same. So we still have the time diagrams and we can use them, we reuse them, and we have the dynamic load cases. And all that's new is now that the explicit solver is active. We are allowed to select it now. So I'm going to copy this case, and rename it to non-linear, and I'm choosing the explicit solver. And also here in these tabs, the user interface is the same. So here's the connection between load cases and time diagrams. The only thing that's missing is here the time step for calculation. As I explained in the introduction, RSTAB is data mining the time step automatically, and it's doing this very well. And you would have here the details. You have a frequency limit here, maximum natural frequency. And just in case you really think you have to use a smaller time step, you can increase the frequency to do so. But usually it works very well. So yeah, because as I said in the introduction, RSTAB reduces the time step further as soon as nonlinearities are detected. So it's not using a constant time step, it's optimizing the time step during calculation. The calculation parameters stay just the same. These mass direction checkboxes are now inactive because the explicit solver requires masses in all directions. So it's not allowed to apply masses only in X direction. And we are going to perform a large deformation analysis. And I want to keep the Rayleigh damping as it is because, as I said earlier, we have just the damping is slightly lower in the frequency range in between. So it's just expected that the structure is slightly lower damped than it was before, and this is on the safe side, so I'm going to keep it. But of course, you can again do the same calculations as we just did and adjust the Rayleigh damping. I calculate this. This takes now a little bit longer than before. Obviously, it's now a nonlinear analysis, and the time step is smaller than for the linear analysis, but still, RSTAB is calculating it quite quickly. So once the calculation is done, we again have a look to the same node and look to the displacement. So I open another case is added here now. We have 2 natural vibration cases and we have 2 dynamic load cases now here in the drop-down list. We are going to look to the dynamic load case 2. And I want to again double check the time course monitor and check the node that we have seen earlier. Clearly, there's no resonance anymore. So this is what we expected. The frequencies do not match anymore. And in between, we double check the tension member, tension only member. And indeed, it's now only having tension in it, and it fails quite often. It's getting reactivated and so on. Back to the node and the displacement in X direction. So this is the displacement. More important when you consider dynamics and vibrations is the acceleration and the velocity. So let's have a look to the accelerations in X direction. We have the root mean square value available down here, and we can have a look to it up to 10 seconds. So we have a mean value of 52 millimeter per square seconds. And when we have a look to the velocities, they're disappeared. No, here they are. Velocities we have in the root mean square value is 1.8 millimeter per second. We have some higher peak values, but the mean values are important. This is okay regarding some limits that are available. When you look in the literature, you find some limits that are coming from us. So these are some human perceptions of vibrations. It could be that you have to reduce the limits even further, dependent on the machines or measuring devices that are in place. So machines or measuring devices are usually far more sensitive than we humans are. So we have limits of accelerations in black. So, and still okay is unpleasant. So this is it shouldn't be any more, at least when we look to the mean values. And so we have 1.3% of G. So this is then approximately 130 millimeter per square second would be okay as a limit of acceleration. And in red, you see the limits of velocities. And here you should have no more than 2 millimeters per second. And back to the example, this is what we full phi. So we are below the 2 millimeters for velocities, and we are also below the 130 for accelerations in X. So due to the nonlinear consideration and due to the fact that there's no resonance occurring anymore. So this was the case tension members that I wanted to show you. And we now want to have a look to a second type of nonlinearity. I want to show you a failure of support. So we study a case of damage. So when I go onto this support, I can create a new type of support. And just imagine it's broken in the horizontal direction completely, so cannot take any force in the horizontal direction anymore, and it can just take pressure, but no uplifting forces anymore. So when I can have a nonlinearity defined here, failure all if negative P set. So the support turns blue. This means there is a nonlinearity defined. All the results obviously are deleted. And when we now go back to DYNAM Pro, I just want to deactivate the natural vibrations You do not have to calculate them anymore. And I want to show you this option. When you deactivate it here, it deletes all your natural vibration cases. And I could do the same with the linear time history analyzers because I do not want to perform it anymore. I do not want to recalculate it. But there is another option that I want to show you. You can have DLC linear analyzers. You can clear this checkbox to solve here on the right-hand side, or you can use your right mouse button and you have some more options here. And you can also here set not to solve, which means it won't be calculated when I press OK or calculate now. In the nonlinear analysis case, I just want to reduce the maximum time, 2, and everything else stays the same. I even want to keep now the Rayleigh damping the same. Okay, and calculate, and then we have a look to the results and check if the results are plausible or not. So again, the cases reduces, of course. There's only the DLC2 available now, and I want to have a look to the time course monitor and look to the support nodes and look. PX and PY are obviously 0 because the degree of freedom it's free movable in these directions, and the support force PZ, it's node 14. We see now 3 peaks, so the support is still active. It's still working up to 0.14 seconds. Then it fails. Then it's shortly reactivated. There's a peak at about 0.35 seconds and another small peak here at 0.6 seconds. Let's double check this and have a look to the deformations. When you click on the node, it jumps over to nodes. You can now just here have the displacement set. It's node number 14. And we can see the same behavior. So as long as the support is active, we don't have any deformations. So this is up to 0.14 seconds. Then we have, of course, some deformations because the support failed. There was another little peak here at 0.35, so no deformation here. And another little peak was here shortly before the 0.6. So again, the deformation is 0. And then the structure is drifting away. All the forces are relocated. And it really comes to some failure. You can also animate this. We have some animation available. So another window pops up, and I want to have to decrease here the scaling factor so that we can see something here. So this is a very large deformation scaling factor now here. When I click to play, you see the graphic, the main graphic moving. You see the line going through the time course monitor. So it's acting all together, and you can really see the structure moving away here. Okay, so it's drifting. Now it starts drifting away. Okay, so this is just the last feature I wanted to show you. Now that's me done with the example today in RSTAB. Just quickly back once more to the slides, just to give you some literature hints. That the first one is in German, but I'm sure there are some in English as well, where you find some hints to acceleration and velocity limits, and also some hints for excitations, machine-induced vibrations. The two, Bate and Chopra, these are theoretical books where you find some more information about the solvers. And of course, we have the manual, which is still from October 2007. It's just in the updating process. So I thank you very much for your attention. I hope it was helpful. And I hand the screen now back to my colleague, Amy. So thank you very much for your attention. Bye-bye.
Thank you, Gerlinde. So I know that was quite a bit of information within the last hour. We always want to encourage you to visit our website at dlubal.com to learn more about dynamic analysis, our modules, and any other capabilities within RFM and RSTAB. As I mentioned before, we have several other additional recorded dynamic webinars available also through the website and on our YouTube channel. And lastly, we have other resources available, such as frequently asked questions. We have our knowledge base, which will include tips and tricks and other technical articles, videos, newsletters, and much more. I did also want to mention that we have several upcoming events and conferences. A few are listed here on the screen. You can find those on our website. If you will be in the area for any of these events, we encourage you to come and visit us so that we can meet you in person. Our email for our German office is info@dlubal.com. Again, that's info, I-N-F-O, @dlubal.com. Our phone number is +49 9673 92030. If you have any questions or comments about today's presentation or anything else regarding our software, feel free to send us an email or to give us a quick call, and we will be happy to help further. With that said, we want to thank you for attending today's presentation, and as always, we hope to see you at the next webinar. Thank you.